Hi, this is Luke from the Stats Medic, and in this lesson we're going to talk about how to calculate confidence intervals for slope. So we only have one learning target here, and that's to construct and interpret a confidence interval for the slope beta of the population regression line. Now we are going to be using the four-step process here, so that means we're going to be going through state, plan, do, and conclude. And a big part of the new stuff in this lesson has to do with the plan and checking the conditions, which will look a bit different than some of the conditions we've seen in previous confidence intervals. So the context of this activity will look very familiar to you. It is the same as the previous lesson, and we want to know, does seat location matter? So if you recall, there was a teacher who randomly assigned their 30 students into 5 different rows at the beginning of the semester, and then recorded their exam scores at the end of the semester. Now there is some information from that first lesson that we're going to need for this lesson, so let's go ahead and record that now. First of all, the line of best fit was the predicted score is equal to 85.95 minus 1.517 times the row. And that line of best fit then, of course, gives us our slope here. So let's go ahead and record that as negative 1.517. And if you recall from the previous lesson, the interpretation of this slope was telling us that for each additional row that we moved back, we predicted that the exam score would go down by 1.517 points. The other piece of information that we have here that we need is the standard error of the slope, and this would be given to us from some sort of computer output. You will need that for later in the activity. Now, before you get started on this activity, let me give you a little bit of a heads up. When you get down to question number 3 here, it is going to ask you to create some graphs here, a scatter plot, a residual plot, and then a dot plot of the residuals. And I'm going to suggest that you use an applet to do that. So you will find it at www.staplet.com, and you will have to choose the correct applet to use here. The correct applet is 2 quantitative variables. So use the applet to help you make those graphs, and you have everything that you need in order to complete the whole activity down to the stop sign here after question number 5. So you're going to do the whole activity and then come back to the video to see what your answers look like. So go ahead and pause the video now. So let's take a look at your answers from the activity. In question number 1, we were asked, if the teacher were to do a different random assignment of 30 students, do you think the slope would be the same? And we have a definite no for this one, and we know this from the previous lesson where we actually shuffled cards into 5 different piles, each time calculating a new LSRL and finding a different slope every time, which was what allowed us to talk about the sampling distribution of B, the slope. Now for number 2, check to make sure that you're using the correct notation here. Beta is our parameter, and B is our statistic. And the other thing I'd like to add in here is that for the parameter beta, the true slope of the population LSRL, I'd like to include some context there. So I'm just going to add in that this is for row and score. I'm just giving the 2 variables, the context of the 2 variables there. Now to the new stuff. There are 5 conditions that we need to check here for inference for slope. Starting with number 1, the linear condition. And I've told you here that you needed a scatter plot as well as a residual plot. And so I'm showing these now on the right. And we can see here from the scatter plot that we do have an apparent linear relationship. May not be a strong linear relationship, but there's definitely a linear relationship there. And the other thing to check is that in the residual plot, you don't have a clear leftover pattern. So when I say leftover pattern, I mean generally like a U shape or an upside down U shape would be bad news. But here we seem to see a fair amount of scatter above and below the x-axis in our residual plot, which is good. So we can say that the linear condition is satisfied. Now for the independent condition, I know that we're used to checking the 10% condition, but let's be careful here. We only check the 10% condition when we are sampling without replacement. And in this context, we did not take a random sample of 30 students. Instead, we randomly assigned those 30 students. So in this particular context, we do not want to be checking the 10% condition. Now, in terms of independence, we do want to know that each observation is independent of the others. In other words, one student's exam score does not have an impact on another student's exam score. So we'll just assume that they're not working together or cheating off of each other on this particular exam. So we'll say the independent condition is satisfied. For the third condition, the normal condition, we now need to check the dot plot of the residuals, which hopefully you got using the applet. And what we're looking for is strong skew or outliers. And based on this particular dot plot, I don't see any strong skew or outliers, so I would say that the normal condition is satisfied. For the fourth condition, equals standard deviation, we need to take a look at the residual plot here, which we already have. The residual plot is right here. And we need to know that it has roughly equal variability at each x value. So when you look at each one of the rows, you want to see just about the same variability. And there is a little bit more variability maybe here than there is here, but we don't see a clear pattern of changing variability here. So we would say that this condition is satisfied. And the fifth condition is one that we're very familiar with, the random condition. And definitely we want to make note here that this is random assignment, and we do not have a random sample. So with our 5 conditions satisfied, we are ready to construct a confidence interval. Now hopefully you know the general formula pretty well at this point, point estimate plus or minus margin of error. The specific formula you had to come up with on your own here. And we know what our estimate is. That's always our statistic. And in this case, our statistic is B. And this one, we definitely want to be using T star rather than Z star. And this has to do with the fact that we don't know the standard deviation of the population for a couple of different things, for X or for Y or for the residuals. So we are definitely stuck using a T star here. And then we're going to use the standard error of B, which was given to us on the top of the page. Now, when we look at your work here, there's something that I want to make a note of, and it has to do with this T star value here. So we know that in order to get our T star value, we have to know the degrees of freedom. And I'm going to guess you may have used n minus 1. Well, it turns out in this context, and this is the only time you will see this in AP statistics, the degrees of freedom is n minus 2. And one of the sort of simplified explanations for this is the fact that we have 2 quantitative variables here that both are allowed to vary, and so our degrees of freedom would be n minus 2. So we need to now go to table B and see what our T star value should be. So let's take a look at table B. And as you know from table B, the first thing that we need to know is our degrees of freedom. And we are now saying that our degrees of freedom should be n minus 2. And so n minus 2 for this particular activity is going to be 30 minus 2, or 28. And so we know that we need to be in this row. Then if we scroll down to the bottom here, we can find our confidence level. And we know our confidence level is 95%. And so here we are arriving at a T star value of 2.048. Now my guess is you may have chosen this one if you used n minus 1. But let's go back to the activity and fix that up. So here's what we need to change. Our T star value should be 2.048. And it turns out that the interval doesn't really change too much because that was a very small change. The only thing that will change here based on rounding is this will become 1.21. So we're ready for our conclusion, which hopefully is pretty automatic for you at this point in the course. We say we are 95% confident, make sure you have the word confident there, that the interval from negative 4.24 to 1.20 captures the true slope of the population LSRL. And we once again are missing some context here. So let's add in that this is the LSRL for row and score. And the other thing I'm going to add in here is some units. So we say negative 4.24 to 1.20, which actually we're going to change that to 1.21. And the units here for slope are change in y over change in x. So that's going to be a change in the number of points on the exam over the row. So I'm going to say points per row. Now remember, at the beginning of this whole activity, we wanted to decide whether or not seat location matters. And so according to our confidence interval, our slope is somewhere between negative 4.24 and 1.21. So does this provide convincing evidence that sitting farther away from the front of the room actually reduces exam scores? Well, the truth is that if you look at this interval, we know that 0 is contained within the interval, which means that we think 0 is a plausible value for the slope. A slope of 0 would tell us that there is no relationship between rho and score. And so we do not have convincing evidence that sitting farther back will reduce scores. So let's see if we can summarize our learning in the important ideas. So we only had one learning target here, and that was to be able to construct a confidence interval for a slope using the four-step process. And so I think I'd like to highlight just a couple of parts involved in each one of the 4 steps. So let's start with the state. And one of the important things there is that we know how to clearly define the parameter using the correct notation. And so the parameter here is beta, and beta represents the true slope of the population regression line. And then you'll remember in the activity that we actually added some context on the end of that. So we would say for, and then we'll give the 2 variables here, x and y, and that's where we would insert the context. And then remember, the statistic that we're going to use for this is going to be the slope of our sample regression line, which is going to be b. Now let's move over to the plan. Now one thing that we didn't mention yet is the name of this procedure. So let's give the formal name of this procedure, which is a 1 sample t interval for slope. And then the big new thing here in this lesson was the 5 conditions that are necessary to do this inference. And I didn't mention this before, but there is an acronym in order to remember these 5, which is LINER. So let's make sure we know what each one represents. L is linear, I is independent, N is normal, E is equal standard deviation, and then R is random. So use the LINER acronym to help you remember the 5 conditions here. As far as checking those conditions, I'm just going to say see previous page in order to know how to check each one of those 5 conditions. And then the do step, let's remind ourselves of the formulas we used here. The general formula for any confidence interval is going to remain the same here. It is the point estimate plus or minus the margin of error. What's new for us here is the specific formula, and the specific formula for estimating slope is b plus or minus t star times SEB. And a couple other items of note, we decided that in order to get this t star value from table B, we had to know the degrees of freedom, which we're going to use n minus 2. And then the other thing I think to note here is that this standard error of B will almost always come from computer output. And then the last part, the conclusion, I think we feel pretty comfortable writing a conclusion for a confidence interval at this point in the course. So let's see if you can apply your learning in a new context here using the check your understanding, which is going to be a full 4-step confidence interval. So go ahead and try this on your own, and then check back on the video to see what our answers look like. So go ahead and pause the video now. Let's take a look at your answers for the check your understanding. Before we jump into the 4-step process, let's start by making sure that we understand each one of the values that's given in the computer output here. The first thing to recognize is that this is always going to be the x variable, which we know from the scatter plot is miles driven. And then the coefficient that comes before that x is the slope value that we're going to need, so that right there is our b. And then if you move over to the next column, the standard error of the coefficient, well, this value right here is the one that we're going to need, and that is the SEB. So those are the two values that we're going to need from our computer output when we look at the four-step solution. Now, as we look at the four-step solution here, I'm just going to go ahead and underline all of the important information, and you should do the same thing on your answer. So in the state, check first that you're using the correct notation for the parameter beta and for the statistic b. And the parameter beta should definitely have some context in there. So we're saying price and miles driven. And the other thing you want to make sure you include in your state is the confidence level that we'll be using for our confidence interval. Now moving to the plan. First, you want to check that you have the name of the inference procedure that we're doing here, which is a one sample t-interval for slope. And then we know that there are 5 conditions that have to be checked here. And I've just used the graphs that are given to me here and just explained in words what I see. So for the linear relationship, you can do it 2 ways here. You could say something about the scatter plot being approximately linear, or you could say that the residual plot shows no leftover pattern. Now for the independent condition, we do have to check the 10% condition on this one because we are in fact sampling without replacement. So you need 2 comments here for independent, one about the 10% condition and one about individual observations being independent. The normal condition, instead of having a dot plot of the residuals like we had in the activity, this time we have the histogram of residuals, which shows no strong skew or outliers. Equal standard deviation, we check the residual plot, and the residual plot shows similar variability for each x. And then the random condition, which we're very familiar with, we know that we have a random sample here, and I've just stolen the words right from the question here and put quotes around them to show that I've taken it right from the stem. Now let's move over to the do part. We have our general formula here, which is true for any confidence interval. And then we have our new specific formula for estimating slope. And then this is where we're going to go ahead and plug in the b value from our computer output and the standard error of b from our computer output. And you do have to calculate the t star value using table b. And hopefully you use degrees of freedom 14, that's n minus 2 there. And you should arrive at a confidence interval of negative 0.217 to negative 0.108, or maybe slightly different depending on how you rounded. For your conclusion, make sure that you're using the word confident and that you have units associated with the slope that we're trying to estimate, and that you have context at the very end. So this concludes this particular lesson. In the next lesson, we'll take a look at significance tests for slope.